Right now, at this exact moment, 31 satellites are orbiting 20,200 kilometers above your head. Each one moves at nearly 14,000 kilometers per hour, completing 2 full orbits of the Earth every single day. Your phone is talking to at least 4 of them simultaneously, calculating your exact position on the planet to within a few meters. You've probably used this system today. To find a restaurant, navigate to a meeting, check how far you walked. You didn't think about it. You just opened the app and assumed it would work. But here's what almost nobody knows about that system. Every single one of those satellites carries an atomic clock. Not the kind of clock you have in your kitchen. An atomic clock so precise it would lose only 1 second every 300 million years. And every single day, those clocks are intentionally set wrong. Not by accident. Not because of a hardware flaw. But by design, based on the calculations of a man who died in 1955 and a theory he published when most of the engineers who built GPS hadn't yet been born. If the people who designed GPS hadn't accounted for Albert Einstein's theory of relativity, your navigation app would drift by approximately 11 kilometers every single day. Not 11 meters. 11 kilometers. By the time you drove to work, the map would show you in a completely different neighborhood. By the end of a week, the error would be so large the entire system would be useless. Today we're going to look at the real physics behind GPS, what it actually is, why it doesn't work the way most people think, and how one of the strangest and most counterintuitive ideas in the history of science became the invisible foundation of a technology that billions of people depend on every day. And by the end, you'll understand something that most engineers, let alone ordinary people, never pause to consider. The device in your pocket is a daily proof that time is not what you think it is. When most people describe GPS, they say something like this. Satellites up in space send a signal to your phone, and your phone figures out where you are. If you press for more detail, someone might mention triangulation, the idea that by measuring the distance to multiple satellites, you can calculate your position in 3-dimensional space. This isn't wrong. It just leaves out almost everything that matters. The full name is Global Positioning System. It was built by the United States Department of Defense beginning in the 1970s, became fully operational in 1993, and was originally designed exclusively for military use. Civilian access came later, and even then the government deliberately introduced errors into the civilian signal, a feature called selective availability. It made civilian GPS accurate only to about 100 meters. That feature was switched off in 2000 by executive order, and immediately civilian GPS became dramatically more accurate. The improvement wasn't in the hardware. It was simply removing the intentional degradation. The system that emerged is remarkable in its simplicity at the surface level and its complexity underneath. There are currently 31 operational satellites arranged in 6 orbital planes, designed so that at least 4 are visible from almost any point on Earth's surface at any given time. Each satellite weighs about 900 kilograms, carries atomic clocks as its most critical component, and transmits 2 things continuously: its own precise position in space, and the exact time that signal was sent. That's the whole system, at the surface. Your phone receives those signals. It calculates how long each one took to arrive. Since the signals travel at the speed of light, 300,000 kilometers per second, the travel time converts directly to a distance. With accurate distances to 4 or more satellites, your phone solves the geometry and determines where you must be. Simple in concept. Almost impossibly demanding in execution. Because for GPS to give you a position accurate to within a few meters, the time measurements must be accurate to within a few nanoseconds. 1 nanosecond is 1/billionth of a second. In 1 nanosecond, light travels about 30 centimeters. If your timing is off by just 100 nanoseconds, 1/10,000,000th of a second, your position calculation is off by 30 meters. That's the gap between the street you're on and the one next to it. This is why atomic clocks are not optional. They're the core of the entire system. But even atomic clocks are not enough. Because there is a deeper problem. And it has nothing to do with engineering. To understand why atomic clocks alone aren't sufficient, you have to go back to 1905 and a 26-year-old patent clerk in Bern, Switzerland, who was thinking about a question nobody else considered worth asking.
Physics in the early 1900s was in a strange position.
The classical equations of Newton had stood for more than 200 years. They explained planetary motion, the arc of projectiles, the behavior of machines.
They seemed complete. And yet, at the edges of that framework, experiments involving light were producing results that Newtonian physics simply couldn't explain.
The speed of light appeared to be the same for every observer, regardless of how fast the observer was moving.
That made no sense within the existing framework. Albert Einstein looked at this problem from a different direction.
Instead of asking what was wrong with the experiments, he asked what it would mean if the experiments were right. If the speed of light really is constant for every observer, what has to be true about space and time to make that possible? The answer he arrived at, published in June 1905 in a paper almost nobody read at the time, became the special theory of relativity.
The central consequence of special relativity that matters for GPS is this: time is not universal. A clock that is moving runs more slowly than a clock that is stationary. Not because of any mechanical failure. Not because of vibration or wear.
Because time itself passes more slowly for objects in motion, relative to objects at rest.
The faster the motion, the more pronounced the effect. This is called time dilation.
At ordinary speeds, cars, planes, even spacecraft like the Space Shuttle, the time difference is so minuscule that no instrument in everyday life could detect it.
But GPS satellites aren't moving at ordinary speeds.
They move at 14,000 kilometers per hour.
At that velocity, time dilation becomes measurable.
A GPS satellite's atomic clock, because it is moving so fast relative to a clock on the ground, ticks slower than the ground clock.
Specifically, velocity causes GPS clocks to lose approximately 7 microseconds per day. 7 microseconds sounds like nothing.
But remember the numbers we established: 100 nanoseconds of timing error equals 30 meters of positioning error.
7 microseconds is 7,000 nanoseconds.
That's a positional error of more than 2 kilometers every single day, accumulating from velocity alone. Without any correction, a GPS receiver would tell you that you're standing in the middle of a building or somewhere in the middle of a field, 2 kilometers from where you actually are. The error would compound. Within days, the system would be worthless.
But this is only half the problem. Because 10 years after special relativity, Einstein had another idea.
And this one was even more unsettling. In 1915, after a decade of work that he later described as the most intellectually demanding of his life, Einstein published the general theory of relativity. If special relativity was strange, general relativity was almost beyond intuition. It proposed that what we call gravity isn't a force at all, it's a curvature in the fabric of spacetime itself, caused by mass. Massive objects don't pull other objects toward them. They warp the geometry of the universe around them, and other objects follow the curved paths that result. One consequence of this, the one that matters for GPS, is called gravitational time dilation. The closer you are to a massive object, the more distorted spacetime is around you, and the more slowly time passes for you. A clock deep inside a gravitational well, close to a massive planet, ticks more slowly than a clock far from that planet, where gravity is weaker. GPS satellites orbit at 20,200 kilometers of altitude. At that distance, they are significantly farther from Earth's gravitational influence than a clock sitting on the surface. As a result, their clocks don't just tick differently because they're moving, they also tick faster because they're higher up.
The weaker gravity at satellite altitude means time passes slightly faster there than on the ground. This effect runs in the opposite direction from the velocity effect. Velocity makes the satellite clocks run slow. Altitude makes them run fast. And the question that GPS engineers had to answer precisely was, which effect wins, and by exactly how much?
When the numbers were calculated, the gravitational effect turned out to be larger than the velocity effect.
Gravity speeds up GPS satellite clocks by approximately 45 microseconds per day. Velocity slows them down by about 7 microseconds per day. The net result is that GPS satellite clocks, if left completely uncorrected, would run fast by approximately 38 microseconds every single day. Let's calculate what 38 microseconds means in practical terms. Light travels at 300,000 kilometers per second. In 38 microseconds, light covers about 11.4 kilometers. GPS works by measuring how long light-speed signals take to travel from satellite to receiver. If the satellite's clock is off by 38 microseconds, the position calculation is off by 11.4 kilometers every single day, with the error growing with every passing second. Without a correction, GPS would be functionally useless within the first day of operation. The satellites themselves would be the source of the error, not any hardware failure, not any software bug, but the universe operating exactly according to the laws that Einstein described. When GPS was being designed in the 1970s, there was genuine debate inside the development teams about whether relativistic effects needed to be addressed at all. Some argued the effects were too small to matter. Others insisted that the calculations were unambiguous, skip the correction, and the system fails. The engineers who took relativity seriously won the argument. And the solution they chose was as elegant as the problem was strange. Rather than correcting for relativistic errors in software after the fact, they adjusted the frequency of the atomic clocks before the satellites were even launched. The clocks were deliberately set to run at a slightly different rate on the ground so that once they reached orbit, the combination of velocity slowing them down and altitude speeding them up would bring them back into near-perfect sync with clocks on Earth's surface. The adjustment was precise. The satellite clocks were set to run at a frequency of 10.23 MHz minus 4.464 MHz. That small fractional correction, built directly into the hardware of every GPS satellite ever launched, accounts for both special and general relativistic effects simultaneously. There are additional software corrections for smaller variations caused by the slight elliptical shape of the orbits, since satellites at the near point of their ellipse experience slightly stronger gravity than at the far point. These residual corrections are continuously applied by the ground control system. The result is that your phone, and every GPS device ever made, is quietly applying Einstein's equations every time it calculates your position. The engineers didn't do this because it seemed philosophically interesting. They did it because without it, the physics of the universe made the system fail. And the system works. There's a comfortable assumption people tend to make about GPS failure, that it's a minor inconvenience. Your app shows you the wrong turn. You recalculate. You arrive a few minutes late. The reality of what GPS failure actually means for modern society is considerably more serious. Modern infrastructure uses GPS for two separate things: positioning, which is the navigation function most people know, and timing, which is invisible but far more critical. These are two distinct services, and the timing function has become embedded in systems that most people would never associate with satellites. Global financial exchanges use GPS timestamps to synchronize trades across networks spanning multiple continents. When markets in New York, London, and Tokyo execute transactions, the timestamps that sequence those trades come from GPS timing. An error of a few microseconds can cause transactions to be processed out of their correct order. At the volumes modern markets operate, that's not a minor issue. Power grids use GPS to synchronize the phase of alternating current across thousands of kilometers of transmission lines. The electricity arriving at your wall socket is synchronized across an entire continent by GPS timing. Lose that synchronization, and the resulting imbalances can trigger cascading failures, the type that produce widespread, extended blackouts. Mobile networks use GPS timing to coordinate handoffs between towers. When your phone moves from one cell to another, GPS timing ensures the handoff is seamless. Degrade that timing, and calls drop and data transfers fail. In January 2016, a software error in a GPS ground control facility caused 69 satellites to broadcast incorrect timing data for approximately 13 hours. The error was small, the timing offset was measurable in microseconds, but it was enough to disrupt timing receivers in certain telecommunications systems. It served as a demonstration that even brief, small errors in GPS timing propagate into infrastructure systems that most of the people affected had no idea relied on satellites. Aviation uses GPS not just for en route navigation but for precision approach and landing systems that allow aircraft to land in near-zero visibility conditions, fog, rain, low cloud, when visual approaches are impossible. The same system that routes a cargo drone in a warehouse operates at a larger scale on every commercial flight. This infrastructure dependence wasn't planned in a strategic sense. It accumulated gradually as GPS became reliable, cheap, and ubiquitous.
Systems were built that used GPS timing because it was available and accurate, without deep consideration for what a failure scenario would look like. Today, most contingency planning for GPS failure is classified or incomplete. The GPS story is the most striking example of relativistic physics embedded in everyday technology, but it isn't the only place where Einstein's equations are running behind the scenes of ordinary life. Particle accelerators, the machines used to study subatomic particles, which led to discoveries ranging from medical imaging to the development of the internet, use relativistic corrections as operational routine. As particles are accelerated toward the speed of light inside these machines, their relativistic mass increases. The magnetic fields used to steer the particle beams have to account for this mass change continuously. Without relativistic corrections, the beams would miss their targets completely. Modern computer processor design has to contend with relativistic effects in the behavior of electrons moving through transistors at near relativistic speeds. At the densities of current generation chips, with transistors measured in nanometers, these effects, though small, become relevant to design calculations. Even the color of gold traces back to relativity. Gold's electrons move fast enough that their relativistic mass increase alters the energy levels at which they absorb light. This shifts what wavelengths of light gold reflects, changing its color from the silvery white of most metals to the characteristic warm yellow associated with value and wealth for thousands of years. Without relativistic effects, gold would look like aluminum. The color of royal jewelry, of ancient currency, of trophies and medals, a consequence of the same physics that corrects your GPS. The nuclear reactions that power the sun are described by Einstein's most famous equation. When the sun converts hydrogen to helium in its core, a small amount of mass disappears and becomes an enormous amount of energy, according to E equals mc squared, the direct consequence of special relativity. The light that reaches Earth, that drives photosynthesis, that grows the food you eat, carries energy that began as mass converted by relativistic physics in a star 150 million kilometers away. Every bite of food you have ever eaten contains energy that Einstein's equations describe. The scope of this is easy to miss because relativity operates in the background. It doesn't announce itself. It just runs. We tend to think of physics as something that happens in laboratories and lecture halls, abstract, distant, belonging to a world of equations and academic papers. We think of Einstein as a historical figure, a symbol of genius from another era. But the truth is different. Einstein's equations are running right now, in real time, in the device most of you are holding. Every time a GPS satellite transmits its timing signal, it is doing so with a clock that was deliberately calibrated to account for the fact that time passes at different rates depending on velocity and gravity. Every time your phone calculates your position, it relies on a system whose designers had to accept that the universe operates according to rules that would have seemed like pure philosophy a century ago, and then engineer a billion-dollar defense system accordingly. The engineers who built GPS didn't add relativistic corrections because it seemed interesting. They added them because the universe required it. The satellites are in orbit. The physics is operating. The corrections exist, or the system fails. There's a broader point here. The most important things shaping your life are often the ones you never see. The satellites above you, the corrections embedded in their clocks, the equations that make a navigation app accurate to within a few meters, all invisible, all essential, all running in the background while you ask your phone for directions to somewhere you've never been before. If this kind of analysis is what you're looking for, the real story behind the technologies and systems running your life, subscribe. What comes next will take you even deeper.